Now that we've defined sine and cosine, we can actually investigate their properties just as functions. So what we're going to do is look at, we know that sine of theta, in terms of our most important diagram, sine of theta is the y-coordinate divided by r. But since theta can be, when you're using radian angle measure, theta is just a number, really, because the unit radians isn't really a unit. It's just a note to ourselves that we're measuring an angle. We can actually regard sine of theta as a function where theta is the input and the output is just some value. So sine of theta, since it's a function, it has a domain and a range and a graph and all the other things that any function would have. So let's figure out what those are. So let's do domain first. Since our input theta can be any angle, we have to ask ourselves for the domain, what angles actually make sense for sine? Well, if you draw the most important diagram here, and let's draw the version that is a unit circle. So we have 1 for our radius, and theta is right in here. In a unit circle, sine of theta is the vertical coordinate of this intersection point with the circle. So that's this green distance, that's the vertical coordinate. So to figure out the domain of sine, we just have to ask ourselves, for what angles is there a vertical coordinate? Well, it doesn't matter what angle you put in this unit circle. You're always going to intersect the unit circle somewhere up here, and that point will have a vertical coordinate. And so there's always some output that comes out of sine here, no matter what angle you put in. And so you can put any angle into the sine function. That means the domain of sine is all real numbers. Same thing goes for cosine, of course. The only difference for cosine is that we would be talking about horizontal coordinates in this diagram instead of vertical coordinates. But still, no matter what angle you put into this diagram, you would get some horizontal coordinate, and that means that cosine of theta is defined for any theta. All right, so now let's think about range. Remember, range is what values come out of this function. So it's vertical coordinates that come out of the sine function. So let's ask ourselves, what vertical coordinates actually show up on this diagram? Well, the largest vertical coordinate on this diagram is up at the top of the circle, and that's +1, because we're on a unit circle. And the smallest vertical coordinate on this diagram is down at the bottom, and that's -1, again, because we're on a unit circle. And so the range of sine of theta goes from +1 all the way down to -1, including +1 and -1. And it does hit everything in between. You can see it does touch every vertical position between -1 and +1. So the range of sine is from -1 to +1. That's actually also true for cosine, because the smallest horizontal coordinate is -1, and the largest horizontal coordinate is +1. So the range of cosine is also from -1 to 1. So that's it for domain and range for the functions sine and cosine. Let's have a look at the graphs. And let's start with sine. So we're going to graph y equals sine of theta. But to have a graph, remember you have to put your input variable on the horizontal axis, so that's theta, and your output variable on the vertical axis, and that's y. So this is not the xy plane that we're looking at here. This is the theta y plane to get a graph of sine of theta. And to get a graph, you do what you usually do. You just plot a bunch of points. So for example, sine of 0 is 0, so we could plot that point here. And then sine of pi over 2 is 1. You could plot that point here. And sine of pi is 0 again. sine of 3 pi over 2 is minus 1, and then sine of 2 pi is 0 again. So this gives you some isolated points, but it's kind of hard to see how these fit together into a graph. So really, to get a good idea of what the graph is, we should look at a lot of points and not just the few that we've drawn here. So to do that, let's look at this diagram. So the way I have this diagram set up, this point A, I can drag it around the circle, and as I do, the vertical coordinate of this point gets copied over to this point here. The horizontal coordinate of this point on our graph of sine actually is going to correspond to the angle that is in the middle of the circle here. Right now the angle is 0, and so the horizontal coordinate of this point is 0. And the vertical coordinate of the point A is 0, and so the vertical coordinate of this other point is 0. All right. Now as I drag the point A upwards, it's not letting me drag this upwards. All right. So the way I have this diagram set up, there's an angle in the circle here. Right now it's 0, so you can't really see it. And as I change this angle by dragging this slider, this point will move around the circle to wherever the angle hits the circle. On this graph on the right, this is the theta y plane. And so theta is the horizontal coordinate here. So whatever the angle is inside of the circle, that will be the horizontal coordinate of this point. And the vertical coordinate of this point in our graph will be the vertical coordinate of the point A in our circle. So right now you can see this angle is 0. That's why you can't see the angle. And the vertical coordinate of the point A is 0. And so this point is at 0, 0 in the theta y plane. If we increase theta a little bit, now you can actually see the angle theta right in here. And the vertical coordinate of A has increased a little bit, and you can see there's a red line segment to copy the same length over onto the theta y plane. All right, so this is what the first part of the graph of sine is. To see what the rest of the graph is, we can just increase theta to make this point go all the way around the circle. So as we increase theta to swing over the top of the circle, then the height of this graph sort of tops out at +1, since that's the top of the range, and it starts to come back down because the point A is starting to come back down on the other side of the circle. And then eventually it reaches 0, and then it goes negative because in this third quadrant over here, y coordinates are negative. And then it swings around the bottom of the circle and starts coming back up. And then it gets back to 0. So this is one complete cycle, one complete trip around the circle for the graph of sine. Of course, the graph of sine, since the domain of sine is all real numbers, this is only one small piece of the graph. If the slider were longer and we could increase theta more, this graph would continue up and to the right, and we just get another copy of this graph sitting further to the right. Okay, so that's for sine. Now let's look at cosine. So let me back this up, and we'll switch to cosine. Now the thing about cosine is, just to make the graph match up with this circle, I have to make it stick downwards instead of sideways. So you might need to turn your head to the right 90 degrees to make this graph look like what it usually looks like, with theta going horizontal instead of vertical. So the theta axis is going down here, and x coordinates are being copied from the point A down onto this graph. Okay, so it looks like when theta is 0, the angle is collapsed down to nothing. The horizontal coordinate of the point A is 1, it looks like, and so cosine of 0 is 1, and that is right. And if we increase theta, the horizontal coordinate starts getting smaller. When the point A is at the very top of the circle, that's when theta is pi over 2, which is about 1.5. We're at the very top of the circle, and so the x-coordinate of that point is 0, and so cosine of this angle is 0. And then as we swing over to the top of the circle, now we're getting negative x-coordinates, so we're to the left of the theta axis here. And as we swing around the left-hand side of the circle, now we've gotten to the most negative x-coordinates, and the x-coordinates start increasing. And then we get back to 0 at 3 pi over 2. And when we've made a complete trip around the circle, we get back to where we started. So these are the graphs of sine and cosine. Let's sketch those just to make sure we understand what they look like. So for sine, sine of theta from 0 to 2 pi starts at 0, increases, decreases, all the way past 0 down to the bottom, and then increases again. This top point is at pi over 2 comma 1. This middle point is at pi comma 0. This bottom point is at 3 pi over 2 comma minus 1. And then we get back to 2 pi comma 0 right here. Now, as I was saying before, if you let your angle increase further past 2 pi, you just go around the circle again, and so the y values that you get repeat. And so there's another copy of exactly the same graph out here. But then, of course, there's another copy if you go around the circle again. And in fact, if you go around the circle backwards, there's another copy of the graph to the left. So the graph of sine looks like this basic sort of wave shape, but it just repeats infinitely many times off to the right and off to the left. For cosine of the graph of cosine of theta, it starts up here. This is at 0 comma 1. And cosine of theta starts out decreasing. When it first hits the x-axis, the horizontal axis, that's at pi over 2 comma 0. And then it goes negative for a while. The most negative value is at pi comma minus 1. Then it increases, it gets back to the horizontal axis at 3 pi over 2 comma 0, and then it gets back to the top at 2 pi comma 1. Just like sine, if you go around the circle again, the x coordinates start repeating themselves, and so this graph actually repeats itself infinitely many times off to the left and off to the right, like that. Okay. So from this exercise, we can actually see a couple things about sine and cosine. So first of all, sine and cosine are both what's called periodic. And that just means they repeat themselves. So both of these repeat every 2 pi. Okay, so another way to say that would be that if you take any sine of any angle, and you compare that to that angle plus 2 pi, these are the same. And also for cosine. Cosine of any angle, if you compare that to cosine of that same angle plus 2 pi, it's the same. Okay, so both sine and cosine are repeat every 2 pi. They're periodic. How long it takes them to repeat, this is called a period. So the period of sine and cosine is 2 pi. Another thing you can see from this picture is that sine and cosine, actually their graphs are pretty much the same shape. It's just that it looks like they've been shifted. So comparing this first top point on sine to the first top point on cosine, it looks like to get the graph of cosine, you can start with the graph of sine and just shift it to the left until the top point gets to the vertical axis. And it looks like this, the distance you would have to shift it is pi over 2, because that's the horizontal coordinate of this top point. So we said that to get cosine, of theta, we start with sine of theta, and then shift left pi over 2. So to get cosine, you start with sine of theta, like this, but then shift left pi over 2. And to shift a function to the left pi over 2, remember, you inside the function, you just subtract the shift that you want. That's a shift right. To get a shift left, we need to add the shift that we want. There we go. So cosine is the same as sine, but shifted to the left pi over 2, like that. Or another way to say the same thing, if you wanted to start with cosine and get sine, you'd take cosine and shift it to the right pi over 2. Okay. So just by looking at the graphs of sine and cosine, we can actually figure out some interesting properties of sine and cosine. We found their domain and range. We noticed that they're periodic with period 2 pi. And we noticed that sine and cosine are actually related. They're just shifts of each other.